This is DAT22103 Cloud Computing, Chapter 5, Safety and Disaster Protection, Part 2. This video will cover the remaining topics of Chapter 5, focusing on disaster protection in cloud computing environments and disaster protection management. We are now starting Section 5.3, Disaster Protection in Cloud Computing Environments. We begin with a topic overview of what disaster protection means. Disaster protection means making sure applications and data keep working and remain accessible, even when serious problems happen. In cloud systems, a disaster is any major event that stops the system from working normally. This can include system failures such as a power cut, network outage, server crash, or even a whole cloud region going down. It can also include human accidents, like wrongly deleting important data, and cyber attacks such as ransomware that locks files or systems. To prepare for these situations, cloud systems focus on two key targets, RTO and RPO. RTO stands for Recovery Time Objective, which means how fast the system must be back online after a disaster. For example, the target might be 1 hour, meaning the system should recover within 1 hour. RPO stands for Recovery Point Objective, which means how much data loss is acceptable during recovery. For example, a system might allow losing only the last 10 minutes of data. For example, a cloud website may store backups in another region. If one server fails, the system can recover quickly, while only losing a small amount of recent data. The main idea is to prepare systems so that they recover quickly and minimize data loss when disasters happen. Next, we will look at the cloud building blocks for protection, which are the infrastructure elements supporting disaster recovery. Cloud systems use several building blocks for disaster protection to keep services running when problems happen. One method is multiple zones or regions, also called redundancy. This means running the same system in more than one location. If one place fails, another location can continue the service. For example, an application may run in Singapore and Tokyo, and if Singapore goes down, Tokyo takes over. Another important method is snapshots and backups, which are copies of data used for data recovery. These copies allow systems to restore data after mistakes or attacks. For example, a company may restore yesterday's database after ransomware or accidental deletion. Cloud systems also use replication, which means copying data to another location. Synchronous replication copies data immediately, with almost no data loss, while asynchronous replication copies data later and may allow a small amount of data loss. Finally, systems use load balancers and health checks, which support automatic failover. The system checks which server is healthy and sends users to it automatically. For example, if server A fails, users are automatically sent to server B without noticing. Together, these technologies help ensure systems stay available and recover quickly when failures occur. Moving on to our next topic, we will discuss common disaster recovery, or DR, patterns. This slide shows common disaster recovery, DR patterns, used in cloud systems to recover services after a failure. The first pattern is backup and restore, also called cold recovery. In this method, only data is backed up, and the system is rebuilt after a disaster. The recovery speed is the slowest, sometimes taking hours to days. The cost is low, but it usually means high RTO and high RPO. For example, a company stores database backups in cloud storage. If the server crashes, IT rebuilds the server and restores the data. The second pattern is pilot light. Here, only important core systems are always running, usually a small version. The rest of the system starts when a disaster happens. The recovery speed is medium, usually minutes to hours, and the cost is moderate, with medium RTO and RPO. For example, a database runs in another region, but web servers start only when needed. The third pattern is warm standby. In this model, a smaller full system is always running and ready to grow. The recovery speed is fast, often in minutes, with low RTO and low RPO. For example, a small copy of a website runs in another cloud region, and when disaster happens, more servers are added quickly. The last pattern is active-active. This means two full systems are running at the same time, in different locations. It provides the fastest recovery, with almost zero downtime and very low RTO and RPO, but the cost is the highest. For example, users may automatically connect to another region if one data center fails. These DR patterns help organizations choose the right balance between cost, recovery speed, and reliability. The final topic in this part is storage and database protection. In cloud systems, storage and databases must be protected so that important data is not lost. For object storage protection, one important feature is versioning. Versioning keeps old copies of files, which protects data from accidental deletion or overwrite. For example, if a student deletes a report stored in cloud storage, the system can restore yesterday's version. Another feature is lifecycle rules, which automatically move older backups to cheaper storage, helping organizations manage cloud storage cost. For database protection, cloud platforms often provide point-in-time restore. This means the database can return to an earlier moment, such as before a mistake or attack happened. Another feature is multi-AZ, meaning the database runs in multiple data centers. If one data center fails, another one automatically takes over, so the service continues running. Another important part is backup quality. Systems should perform consistency checks to make sure backups are not corrupted. They should also perform restore tests, which confirm that the backup can actually be recovered when needed. The key idea is simple. A backup is useless if it cannot be restored. Cloud protection is not only about saving data copies, but also ensuring those copies can truly bring the system back after a problem. Next, let's explore network and compute resilience within infrastructure. Cloud systems must stay available even when traffic increases or a server fails. This is called network and compute resilience. One method is auto-scaling across zones. The system automatically adds or removes servers in different locations to handle traffic or failures. For example, if one server becomes busy or goes down, new servers start in another zone. This helps websites stay online during high traffic, such as during an online sale. Another method is stateless services. This means servers do not keep user data inside themselves. Instead, user sessions are stored in shared storage, such as a cache or database. Because of this, if one server crashes, the user does not get logged out, since the session information still exists in shared storage. The third method is health checks and rolling updates. The system checks servers regularly and replaces broken ones automatically. Updates are also done one by one, not all at once. For example, the system may update server A first, then B, then C, so the website never fully goes down during an update. Together, these techniques help cloud systems remain stable, handle traffic smoothly, and continue running even when problems happen. The next topic is about protecting systems against human error. Cloud systems must also protect against human error, because mistakes can happen. The goal is to reduce damage caused by mistakes, such as wrong delete, wrong setting, or wrong command. The first method is least privilege access using IAM. This means users get only the permissions they need, not full access. For dangerous actions, the system may require approval, such as deleting a database or shutting down servers. For example, a student may view files, but only the admin can delete them. The second method is recycle bin and versioning. The system keeps deleted files for some time before permanent removal. It also stores older versions of files and configurations. For example, if someone accidentally overwrites a report, the system can restore yesterday's version. The third method is infrastructure as code, or IAC. This means the system setup is saved as code files, including servers, networks, and storage. If something breaks, the system can rebuild everything automatically. For example, if a wrong setting crashes the system, engineers can redeploy the system using the saved template. The key idea is simple. People make mistakes, so systems should be designed to recover from them. Now let's look at the strategic overview of balancing cost versus protection. Cloud protection always involves a balance between cost and protection. The goal is to balance the money spent with how important the system is. The first step is classify each application. We ask simple questions. How many users depend on it? What happens if it is down? How much data can we afford to lose? These questions help us understand how critical the system is. The second step is choose a protection tier. The highest level is Gold for critical systems. It uses active-active protection, where systems run in multiple locations at the same time. Downtime is almost zero, and data loss is almost none. A real example is online banking or payment systems, where services must always stay available. The next level is Silver for important systems. It uses warm standby protection, where a smaller system is already running and ready to take over. Downtime may be minutes to hours, and the cost is high. An example is an online service portal used by many customers. The third level is Bronze for non-critical systems. It uses backup and restore. If something fails, the system is rebuilt, and data is restored from backups. Downtime can be hours to days, but the cost is lower. Examples include internal reports or test systems. The key message is, spend more protection on systems that can cause big damage if they fail, and use cheaper protection for less important systems. We will now examine a mini case study on disaster protection design for a registration portal. This mini case study shows a registration portal disaster protection design. The problem happens during peak registration week, where system downtime is unacceptable. The recovery targets are RTO 15 minutes, meaning the system must be back in 15 minutes, and RPO 5 minutes, meaning only 5 minutes of data loss is allowed. The solution design uses warm standby in another region, database asynchronous replication, and versioned object storage with cross-region copy for files. For operations, the team performs a failover test every semester. The lesson is simple. High-impact systems need stronger protection and regular testing. Finally, we will review the basic runbook steps for when a disaster hits. When a disaster happens, teams follow basic runbook steps. First, declare the incident. Confirm there is a real outage and assign roles, such as leader, database, network, and communication. Second, switch users to the backup system, also called failover. For example, engineers may change DNS or redirect traffic to the standby server so the service returns quickly. Third, check system health. Make sure the database is running and test login, main features, and data access. Fourth, inform users. Tell them what happened and share the expected recovery time. Finally, after recovery, review and improve. Do a post-mortem, fix the root cause, and update the runbook so the team is better prepared next time. Here is a summary of disaster protection in the cloud. To summarize disaster protection in cloud systems, there are a few important ideas. First, know your targets, RTO and RPO. RTO means how fast the system must be back online. RPO means how much data loss is acceptable. Second, use more than one location. Systems can run in multiple regions or data centers, so if one site fails, another site can take over. Third, always have backups and test them. Take regular backups and practice restoring them, not just storing them. Fourth, choose the right design for your situation. Match your risk level and budget. High-risk systems need stronger protection, while low-risk systems can use simpler setups. Finally, practice before a real disaster happens. Teams should test failover regularly, so everyone knows what to do when a real incident occurs. We are now in Section 5.4, Disaster Protection Management. In cloud computing, disaster protection is not only about technology such as backup tools or recovery systems. Organizations must also manage how they prepare for problems and how they respond when something goes wrong. This is why disaster protection involves people, process, and policy. People are the staff who know what to do if a system failure happens. Process refers to the clear steps used to restore the system. Policy sets the rules for backups, data protection, and recovery procedures. The aim is to plan, execute, and improve disaster protection. Organizations prepare before a problem occurs, respond during the incident, and then review what happened to make the system stronger. For example, a university cloud system that stores student records may perform regular backups. If the system suddenly crashes, the IT team can follow the recovery process and restore the data so the system can continue operating. During a cloud system disaster, the team should assign clear roles and responsibilities so the response can run smoothly. First, assign an incident commander who will lead decisions and manage the timeline of actions. This person coordinates the team and decides what should happen first, next, and later during the incident. Next, assign a communication lead who will update stakeholders and users. This role keeps everyone informed about the situation, including managers, customers, or system users. Then, assign infrastructure or application leads who will perform failover and fixes. Failover means switching the system to a backup server when the main server fails so the service can continue running. These team members focus on restoring the system as quickly as possible. Finally, assign a recorder who will log actions for the report. This role records what happened and what actions were taken so the team can review the incident and improve future responses. Disaster protection in cloud computing also depends on clear policies and classifications. These help organizations decide how important each system is and how it should be protected. First, organizations classify systems as gold, silver, or bronze, with target RTO and RPO. Gold systems are very critical and must recover very quickly. Silver systems allow a little more recovery time, while bronze systems are less critical. RTO, or Recovery Time Objective, means how fast the system should be restored. RPO, or Recovery Point Objective, means how much data loss is acceptable. Next, organizations define backup frequency, retention, and where copies live. This means deciding how often backups happen, how long they are stored, and where the backup copies are kept, such as in another cloud region. Finally, approvals are required for risky changes to DR components. DR means disaster recovery. These approvals usually come from IT managers, system administrators, or security teams before any major change is made. For example, a cloud banking system may be classified as gold because it must recover very quickly if a failure occurs. Runbooks and playbooks are step-by-step documents that guide the team during a system problem. Instead of guessing what to do, engineers can follow clear instructions. For example, the document explains how to failover, how to restore DB, how to switch DNS, and how to roll back. How to failover means the steps to switch the system to a backup server when the main server stops working, so the service can continue running. How to restore DB means the steps to restore the database from a backup if the data becomes lost or corrupted. How to switch DNS means the steps to change the internet address settings so users are redirected to another working server. How to roll back means returning the system to a previous stable version if a new update causes problems. These documents should also include screenshots or commands, contacts, and time estimates. Screenshots or command examples help engineers follow the instructions clearly. Contact information shows who should be called if help is needed. Time estimates help the team understand roughly how long each recovery step may take. They should also be kept in version control and reviewed quarterly. Version control records any changes made to the document, so the team always uses the latest version. Reviewing the runbooks every few months helps ensure the instructions still match the current cloud system configuration. Another important part of disaster protection is testing and drills. This means practicing how to respond to a system failure before a real disaster happens. These exercises help teams check whether their recovery plans actually work. One method is tabletop, where the team talks through a scenario. The team discusses what they would do if a cloud system fails and how each person should respond. Another method is game day or chaos, where the team performs real failovers in staging or production windows. In this exercise, the team intentionally creates a small system failure and then practices switching the system to a backup server. This helps confirm that the recovery process works in a real environment. During these tests, the team should measure time to detect, time to recover, and errors. Time to detect means how long it takes to notice the problem, while time to recover means how long it takes to restore the system. After each test, lessons learned should be recorded and the runbooks updated so the recovery plan continues to improve. Another important part of disaster protection is monitoring and early warning. The goal is to detect problems early, before they turn into major system failures. One method is using dashboards for latency, error rate, saturation, and cost spikes. These dashboards show the system condition in real time. Latency means how long the system takes to respond. Error rate shows how often requests fail. Saturation means resources like CPU or memory are reaching their limits. Cost spikes help detect sudden increases in cloud spending. Another method is synthetic checks from multiple regions. This means automatic tests are sent from different locations to check whether the service is still reachable for users. There are also alerts tied to on-call rota with escalation rules. This means engineers take turns being on duty to respond to system alerts. If the problem cannot be solved quickly, the alert is escalated to a more senior engineer or manager. For example, if a cloud website suddenly becomes slow, the monitoring system can detect the issue and send an alert so the team can fix it before users experience a major outage. Another important part of disaster protection is change and configuration control. This helps ensure that system changes do not accidentally create new risks. One practice is to use infrastructure as code with pull requests. Infrastructure as code means system settings, servers, and networks are written as code files. When someone wants to make a change, they create a pull request. A pull request is a request for other team members to review the change before it is applied to the main system. This helps detect mistakes and prevents risky changes. Another control is using guardrails, which are policies that block risky configurations, such as creating public storage buckets that could expose data to the internet. Teams should also keep DR environments in CI/CD so they stay current. CI/CD means continuous integration and continuous deployment. It is an automated process that updates and deploys system changes regularly, helping ensure the disaster recovery environment always stays synchronized with the main system. For example, if a company updates its cloud server configuration, the same update can also be applied automatically to the disaster recovery environment so it is ready if a failure occurs. Another important part of disaster protection is compliance and evidence. Organizations must keep records to show that their recovery plans and security controls are working properly. First, teams should keep proof such as backup logs, restore reports, and drill records. Backup logs show when data backups were performed. Restore reports show whether the system can successfully recover data. Drill records show the results of disaster recovery practice exercises. Next, organizations should map controls to standards or policies, such as PDPA or ISO 27001. This means the disaster recovery process follows recognized security and data protection guidelines. Finally, teams should provide auditable trails for management reviews. This means keeping clear records of system actions so managers or auditors can review what happened. For example, a cloud company may keep backup reports to prove that its systems can recover data if a failure occurs. Another important aspect of disaster protection is vendor and contract considerations. When using cloud providers, organizations must clearly understand the services and support they receive. First, it is important to understand the provider SLA or SLO, region scope, and limits. SLA means Service Level Agreement, which defines the expected service reliability. Region scope explains where the cloud service operates, and limits show what the provider can or cannot support. Next, organizations must ensure support plans and contact paths are clear. This means knowing how to contact the provider quickly if a system issue occurs. Finally, teams should plan for data residency and egress during failover. Data residency means where the data is stored, while egress refers to moving data out of the cloud system when switching to another region. For example, a company using AWS should know which region stored its data and how support can be contacted during a system outage. Another important part of disaster protection is having a clear communication plan. When a system problem happens, people need to receive clear and timely information. First, teams prepare pre-approved message templates, such as messages for incident start, update, and resolved. These templates help the team send information quickly without needing to write new messages during an emergency. Next, the plan should define communication channels such as email, status page, chat group, or classroom notice. These channels help ensure the message reaches users and stakeholders. It is also important to set the frequency of updates, for example, every 30 minutes, until the issue is resolved. This keeps users informed about the recovery progress. For example, if a cloud learning system becomes unavailable, the team can quickly send an update to students through email or a status page while the system is being restored. Another important aspect of disaster protection is budgeting and FinOps. FinOps means financial operations, which focuses on managing and controlling cloud spending while using cloud services efficiently. First, teams should estimate the cost for standby environments, storage, and drills. A standby environment means backup servers that are ready to run if the main system fails. Storage is needed to keep backup data, and drills are practice exercises for disaster recovery. Next, teams should use cost alerts so failover does not explode the budget. Cost alerts notify the team if cloud spending suddenly increases during system recovery. Finally, organizations should periodically right-size DR resources. This means reviewing disaster recovery resources and adjusting them so they are not too large or too small. For example, a company may monitor the cost of backup servers in the cloud to ensure the disaster recovery system stays ready without spending too much money. Conduct a blameless post-incident review to understand what happened, why it happened, what helped, and what slowed recovery. Create concrete actions with clear owners and dates, and track these actions to closure, sharing the learnings with the team. In summary, disaster protection management relies on policy, people, and practice. Test regularly, measure recovery metrics, and communicate clearly. Finally, commit to continuous improvement through regular reviews and automation. Thank you. Remember that cloud computing turns computing into a utility, just like electricity.